We're going to start talking now about perturbation theory and really thinking about perturbations, asymptotics, approximations for solving different types of problems that arise in engineering sciences and physics and in overall scientific endeavors. So perturbation theory is all about the art of approximation theory. So really, approximation theory kind of is this art. A lot of methods have been developed in which you can use, the way to maybe casually state this is that you use nearby easy problems to solve harder problems. So the idea is to take a problem which you actually know how to handle completely, and the hope is that there's some problem that's nearby it. Nearby it, we'll talk about what that means. In other words, it's perturbably close so that you can rely on or exploit solutions to problems that you know to help you understand a much harder problem where the only thing you have recourse to is maybe simulations, but you would really like to get some analytic understanding of the behaviors, the dynamics, or the boundary value problem behaviors that are there in that problem. And so we're going to use this idea of perturbation theory to get at this. And what perturbation theory is exactly what it sounds. You take a problem and you perturb it a little bit and try to understand how does that perturbation change the nature of the solution. A lot of times the problem we're perturbing is a linear problem so that I can actually solve it explicitly, and so then I can understand if I, for instance, have a weak nonlinear effect, how does that weak nonlinear effect change the linear dynamics? So this is the main philosophical concept behind this idea of perturbation theory. And so we're going to run through in a series of lectures a lot of the key ideas and mathematical architectures that have been developed towards trying to, in fact, quantify the effects of perturbations on systems. So this applies equally to initial value problems and boundary value problems. So an initial value problem here is something like this. I have some LU. So again, I'm going to let this L represent a generic linear operator. Okay, and here this operator would be a time operator. And so the idea would be that I want to understand, maybe my base scenario is that I have some linear dynamics plus epsilon f. And this f is sort of some generic nonlinear function, and epsilon is small. This is going to be the big trick here. I'm going to assume that I have a small perturbation. So when epsilon is 0, of course, I can solve this problem. And as epsilon is small, there's still the ability to potentially use the solutions I found for an epsilon equals 0 to help understand epsilon not equal to 0. And again, here I'm solving this thing from time 0 to infinity, and with some initial conditions. And for instance, if it's a second order operator, then I'd have some initial conditions like this, where I prescribe the initial state of the system and watch it evolve. I can also frame this in terms of boundary value problems, which we've been looking at quite a bit, which is LU is equal to some perturbative right-hand side term. And again, this is some linear differential operator that exists on some domain 0 to L. So I have some prescribed boundary value problem with some boundary conditions, and here they would be prescribed at 0 and L, which are the two endpoints of this thing. And I want to understand what happens when I have this f present. And the idea is if when epsilon is 0, I maybe can solve this very easily. But as I make epsilon non-zero and turn this f on, this becomes a very difficult problem because I can get some very complicated dynamics here, including nonlinear terms, which create very distinct and different qualitative behaviors to the system. So that's the main idea. I want to start developing a suite of perturbation techniques that allow me to investigate either initial value problems or boundary value problems and to understand how these perturbations fundamentally change the solutions that I have that are near some place where I actually know exactly how things behave. So here's the main idea. It's all about an expansion. It's about saying my solution, U, to these problems, either, again, initial value problem or boundary value problem, is U naught plus epsilon u1 plus epsilon squared u2. And so epsilon is small. And so the idea is I'm building a cascading structure of the hope where u0, which is often called the leading order solution, is the dominant term that I observe in the behavior. And then I get corrections to it. Epsilon u1. Well, the u1 is some kind of function here, but the epsilon tells me that if epsilon is small, it's an order of magnitude smaller than this leading order solution u0. So it's a correction to u0. So u0 is an approximation, and I improve the approximation by adding u1 to it, and I can prove it even further by adding epsilon squared u2 to it. In other words, the idea is that these are a successive set of approximations, a hierarchy, that helps me improve my ability to construct a solution. And this holds, of course, for epsilon is much less than 1. There are a lot of issues around, does a series like this converge? And in fact, often in perturbation theory, it does not converge. It's not like a Taylor series expansion, where if you Taylor series expand to infinity, for some function around some point, there is some finite value this takes. Oftentimes these approximations will create series expansions that in fact diverge. Okay? And so we'd have to look at the properties of u1 versus u2 versus u3 to understand if I have some convergence or divergence issues. But oftentimes I'm never going to compute an infinite sum. I'm just going to compute maybe the first correction, maybe the second correction to my leading order solution, which is u0. Okay, so I'm never thinking about this perturbation theory, about really constructing an infinite series. I'm just really interested in using the fact that I could actually construct a u0 and get a correction to it. And we'll show this as we go through in different examples and how we might do this. So let's talk about the expansion procedure, and let's do this in terms of the time-dependent problem first, which is I had, if you remember, L is equal to epsilon f, and so but now LU is, this u is u0 plus epsilon u1. I expand it here. And then epsilon, I expand it here. And notice now, in order for me to try to understand this, I'm going to have to do Taylor expansions of both the left and the right-hand sides. And same thing happens with the initial conditions. The initial conditions are also expanded. And the idea here is I'm going to expand everything. And what I'd really like to do is start to collect terms that are of the like size. In other words, all the terms that have an epsilon in front of them, they're order epsilon. That's the notation we're going to use. That means that's about the approximate size of those terms. And we want to group all the terms together in a meaningful way. So here's how we would do this. The order 1 terms are the terms that essentially they're not small. And if you go back to this case here, if you do an expansion around here, Taylor expand around here, you get LU0. And this is already size epsilon because I have the epsilon in front. And then here I have some order 1 terms here. And so if I collect those, the order 1 behavior is LU0 is equal to 0. So that's the dominant behavior. And if I collect all the terms that are size epsilon, here's what they are. LU1 is some other terms here. So notice a couple things. When I do this expansion, because the left-hand side is linear, I get the same linear operator here, LU0, LU1, LU2, all the way down. And then I just get different right-hand side terms. And I also have to expand the initial conditions. And notice here that U0 0 is A, the derivative of U0 at 0 is B, and all the initial conditions for all the higher terms like U1, U2, all the way through the event are 0. So this is a formal technique. It is simply making an assumption about the expansion, collecting terms, and then notice what I've done. I've set myself up, instead of solving the original problem, I'm setting myself to solve a hierarchy of linear problems. Now, presumably, linear problems are easier to solve than nonlinear problems. So even if I have nonlinearity in there, it gets buried in these higher order terms as inhomogeneous right-hand side terms. Okay? But I'm not directly solving a nonlinear problem. I'm solving a series of linear equations, and I've turned it into a hierarchy of linear equations. So here's my solution form, technically speaking. It is sum from 0 to infinity, epsilon and u of n. So that's the idea, is right, that you can basically just keep getting progressive corrections to this and keep working your way down through this hierarchy. But in practice, this is not really what you do. In practice, you might do something like this. You simply say, look, when I have my solution u is the leading order solution plus, let's say, the first correction. Oftentimes, it's very hard just to even get that first correction, plus what we call often higher order terms. In other words, everything else beyond that is order epsilon squared, because it has an epsilon squared in front of it. Okay? And of course, we're going to show that sometimes this will have a range of validity of how well does this approximation hold for how long. But this is the main concept, is the perturbation theory is just, it's not about doing something like this, computing an infinite series. It's about doing really just this, compute a correction, a first correction or a second correction to improve your understanding of the problem. And it turns out a lot of these perturbation methods really reveal a great deal about the physics and engineering principles that are underneath all of this that we're studying, all of the kind of equations that we're studying. So that's why it's such an important factor for us to consider. And in fact, a lot of asymptotics and perturbations were sort of the workhorse of the 1960s when we didn't have recourse to doing computational methods, right? We didn't have computers widely available, and they couldn't solve a lot of the problems we were looking at. So we really required the art of approximation to get understanding for many of our physical systems. And so we've made a great deal of progress in understanding systems just by doing these kind of approximation techniques. So let's work through a regular perturbation expansion. And by the way, there are going to be different types of expansions. There are going to be singular perturbation expansions. We're going to do lots of different types of methodologies that are kind of the canonical methods that you might use for doing perturbation theory. And so here what I'm going to do is I'm going to consider something like a partial differential equation, du dt equals n, and this can be some nonlinear function of u, ux, uxx. So this is sort of, in some sense, an uber representation of what we want to be doing with perturbation theory. And so we have this space plus epsilon g. So I put the epsilon here. So it's telling you is that the g there is some kind of perturbation to this base underlying set of equations. Now the base equation itself is nonlinear. So I have du dt equals n. Plus, I'm going to now perturb it with this term here. And the question is, how does this term, if I add it into the physics, actually change the physics? And that's the kind of question we're trying to address in solving this kind of problem. So we're going to take that as our way of looking at this, and we're going to just do exactly what I just said. We're going to take it, we're going to expand. We're going to plug this u into this set of equations up here, expand, and collect powers. Now, here's what happens at the different orders. And I've only given up to order epsilon squared. But the first order term is here. Du naught dt is equal to n. And this is some nonlinear PDE. But the idea is I might be able to solve that. That's my base case. What I can't solve is when you add that g onto this thing, right, back here, right? So I don't know how to solve it with this g. I'd like to understand if I perturb it with this g, what happens. And so here, I'm basically taking this, plugging it in. I have a nonlinear equation at the leading order, but at each order subsequent to that, I have du and dt is equal to linear operator L, which is a function of u naught, u1, f1. Du dt is same linear operator, u2, f2 with some right-hand side forcing. Now, what we've been covering is, hey, what happens if I force a system? And I have a linear operator and I have a forcing. And what we know is that we're going to have to take care of some solvability conditions. And in fact, what we're going to find out, and we're going to work with this quite a bit, we've been talking about this quite a bit, is that those f that are there are going to have to satisfy the Fredholm alternative theorem. So if I'm going to look at this linear operator L, this linear operator L is going to be very instructive in helping understand what's going on in the dynamics and the physics. So L itself, if it has a null space, in other words, we're going to look at its adjoint null space actually, and if its adjoint null space, V, has to be orthogonal to the forcing function f. So this is the condition for solvability that we have to enforce in this hierarchy of constraints. And notice what it does. It forces f1 to be orthogonal to the adjoint to the null space, forces f2 to be orthogonal to the adjoint null space. All of them have to be orthogonal to that adjoint null space. This is a condition required for solvability. And what we're going to see as we go through these calculations is the effect of imposing this solvability condition. Okay? So that's a generic structure. And then let's talk about actually doing a simple example to illustrate this. So the example I want to do is this one here. It's UTT minus U is equal to epsilon U squared. So what I have here is a linear behavior at leading order. And then I have some nonlinear term, which is perturbed, which is perturbatively added. So epsilon U squared. So a little bit of quadratic nonlinearity. I have some initial conditions. There they are. States what the position and the velocity are initially. And then the question is, how do we start analyzing this problem? So we took this, we have this nonlinear problem, but the epsilon is small, so we can take that nonlinear problem and using this perturbation theory, turn it into a hierarchy of linear problems. That's the whole idea. So the order 1 problem, here it is. It's U naught TT minus U naught. It's the linear problem that I highlighted. Just set the epsilon to 0, and that's it right there. There's its initial conditions. At the next order, you get this linear operator, same as we had before, but the right-hand side now is U naught squared. Next order, the operator is 2 U naught U1 with these initial conditions. So now I'm starting to build a hierarchy here, and so I could solve for U naught from here, use it here as a right-hand side forcing to solve for U1, use the U1 and U naught to solve for U2, and so forth. So at every order, I'm relying on the previous orders for their solutions for me to solve at that order. And that's how this hierarchy of linear problems works in perturbation theory. And it's sort of this generic feature that shows up in all these perturbation problems. Okay, for that problem, by the way, the leading order solution you can write down. You can compute it with the initial conditions, and there it is. That is the leading order solution if you just simply set epsilon into 0 and say there's no nonlinearity whatsoever. But if I have a little bit of that quadratic nonlinearity, then I have to ask the question, what is the impact of that on the solution? Well, if you go and put that into the perturbation theory, here is the next order correction. This is what you get out of this thing. Okay? Now there's a couple things to notice here. So you have a few terms that have the exponential e to the t and e to the minus t growth, which is exactly what you had at leading order. But because of the quadratic nonlinearity, notice what you get here. Now you get the e to the 2t and an e to the minus 2t. And this is a consequence of the fact that you have a u squared driving the system. So when you put your leading order solution into there that has an e to the t, if you square that, that's e to the 2t, and it shows up in these solution forms. So this is something that you can do. So your solution is this, and plus epsilon of this. And you can already see it gets fairly complicated. If I were to go to U2, to solve for U2, I'd get even more terms in that solution form. So this is how you would approach this problem. Each hierarchy becomes more and more intensive in terms of solving the inhomogeneous problem that arises. So, and specifically here. So every time I go up in order, the inhomogeneous problem I get is expanded. Because, for instance, I had u naught squared here. Now I have u naught times this u1, which is very large. So now the inhomogeneous solutions to this are quite large that I have to compute. Okay? So you're paying a big price every time you go up in trying to get a better correction. So what about boundary value problems? That was a time-dependent problem. Let's do a simple look at a boundary value problem. Here it is. Same structure, uxx minus u with a little bit of quadratic nonlinearity, epsilon u squared. And then you ask the question, what's the impact of that u squared? Here are the boundary conditions. At 0, it's A. At 1, it's B. And so you can start, again, expanding and writing down your hierarchy. So at order 1, here is the leading order solution for the u naught with those boundary conditions. At u1, here it is. You get this linear operator again, u0 squared on the right-hand side, those boundary conditions, u2, right-hand side, those boundary conditions. And by the way, those right-hand sides, they better be orthogonal to the null space of the adjoint operator. That's the only way you can get solutions to this. Okay? So we're gonna start considering that. So by the way, the leading order solution to that one, they're again exponentials, very much like the time, version of this. And there you go, e to the x, e to the minus x terms with some constants in front. And then you can compute the next order correction, which here you go. There again, the quadratic produces e to the 2x, e to the minus 2x. And I didn't even bother to calculate these coefficients C1 through C5 because they're just very long expressions. It's not clear you learn that much from them, except that you do have these kind of canonical terms that arise that are generated by that quadratic perturbation, right? That correction starts to generate new physics or new terms and behaviors. I also want to consider another problem, which is what happens if I perturb an eigenvalue problem. And so here's my eigenvalue problem. It's very close, similar to the form I had, but now instead of this being a constant, it's lambda is equal to epsilon fu. And then the question is, what happens under perturbations given by f? And here, in fact, are my boundary conditions. So this eigenvalue problem actually shows up quite a bit in electrodynamics, quantum mechanics, and a lot of what quantum mechanics is interested in is what happens if you perturb a potential in which you have electrons in. And in that case, you want to understand what is the shift in the states of the system, in the quantum states of that system due to the perturbation. And so the lambda tend to be, when you find these eigenvalues, they are in fact the energy levels in which atoms sit. And when you perturb it, it shifts what those energy levels are. And we can start to understand it by doing perturbation theory on this and start to understand, here's my perturbation, what are the shifts in the eigenvalues? So in this case, when you do the expansion, you're not just expanding the solution here, you're also expanding the eigenvalue. So the eigenvalue is lambda naught plus epsilon lambda 1 plus epsilon squared lambda 2 and so forth. So you have these expansion terms, and you're going to plug all that into that eigenvalue problem and start to collect terms at each order to see what is the corrections that happen not only to the solution itself, but to the eigenvalues themselves. All right, so here's just the first two orders. So order 1 here. Here's the leading order equation, boundary conditions. Here is the next correction. And notice I have the same linear operator on the left-hand side as the leading order condition. But now on the right I have fu0 minus lambda 1 u0. And by the way, this better be orthogonal to the null space of the adjoint operator, right? So I have to satisfy solvability. So the leading order solution to this, by the way, is easy. I mean, if you look at this here, you know, the solutions to this, these are sines and cosines, but only sine satisfies those two boundary conditions. And in fact, it's on the domain 0 to 1 satisfied. So my solutions are sine n pi x. This satisfies the boundary conditions and the differential equation. Okay? So, and then at the next order, what you have as the solution is u1xx, n squared pi squared u1, f evaluated at u0, and u0's a and a sine n pi x, minus lambda 1 u0, which is a sine n pi x. Okay, so I don't really know what f is, but if I were to prescribe an f to you, what I'm going to do is actually expand that f in terms of these leading order solutions, which are this sine n pi x. So what I can do is say f is a Fourier series, which is a of m sine n pi x. So suppose I could actually compute this. So if I give you a specific f, I could actually compute all the a of m's. And so I'm going to have this representation of f in terms of these basis functions, which are sine m pi x, which are essentially the eigenfunctions of the system. And since it's Sturm-Liouville, this will be a complete set, and I can represent any function f in terms of it that lives on that domain. And so that's the representation. And if you look back at the eigenfunction expansion lectures, I can tell you exactly how to compute that A of m. Okay? And so if I put that in, what you find is you say, here's the left-hand side of the equation, u1 xx, n squared pi squared u1. And then I have A of n. I'm going to pull out the nth term out of that Fourier series, bring it over here, A of n minus lambda 1a sine n pi x, and then the rest of the terms from that Fourier series. Now, why did I isolate the sine n pi x? Because that sine n pi x is sitting in the null space. And I need this right-hand side to be orthogonal to the null space. But this is in the direction of the null space. So the only way to make this disappear and allow me to have solvability conditions satisfied is if an minus lambda 1a is 0. And so what I do is I say, OK, since that's sitting there in the null space, and it does not allow me to satisfy solvability, then what I can do is pick lambda 1 to be A of n over a. And if I pick lambda 1 to be A of n over a, this is 0. This drops out, and now I can solve my solution because I no longer have this issue of violation of the Fredholm alternative theorem. So this is a nice little example already starting to show us how we're going to start seeing that the null space and solvability issues are going to repeatedly come into play for us, and that we're going to have to zero them out in order for us to continue on the hierarchy of getting approximations. And so that's the illustration of that there with this very simple problem. And then, by the way, the solution then for this problem would look something like this. So if you actually solve for u1, it's some arbitrary constant c, because this is the null space, plus the Taylor series expansion given there on the right. So this is how we start going about problems. And all I wanted to do is sketch out a little bit how this starts to look. So perturbation theory is about making an approximation that epsilon is small and expanding your solution in u0 plus epsilon u1 plus epsilon squared u2, plugging it in, collect terms of like powers, and then start to solve this hierarchy of linear equations. So you're trading out solving nonlinear equations, which can be very difficult to do or impossible, to solving a hierarchy of linear equations, which you can do even if it requires a great deal of manipulation. And even in solving this linear hierarchy, you have to make sure that you're not violating the Fredholm alternative theorem as you go through that process. And in fact, enforcing the Fredholm alternative is often what gives you a remarkable amount of information, as we'll see as we progress in these lectures on perturbation theory.